So, welcome everyone. A very, very warm welcome. This is going to be a talk where you will hopefully go out a bit more informed about what cross-modal transfer in the context of protest detection is. We will share our novel approach of how to conduct protest detection. We'll also talk about how you could potentially save your time and money, so make sure to listen carefully. Of course, we'll share our findings and main takeaways on the topic. Worth to mention is that this talk is based on a paper that we presented last December at EMNOP's workshop CASE, focusing on protest detection. But before we dive any deeper into it, we'd like to present who you'll be listening to today.
And as you might have guessed, you will hear this talk from the two of us, being here representing the company Recorded Future. We're also the two main authors of this paper, but we had some support from our colleagues. And my name is Kajsa Andreasson, and I'm working as a software engineer in the NLP team at Recorded Future.
And my name is Ria Raj, also working at Recorded Future as a software engineer, but in the threat intelligence domain. And the idea for our paper that we presented was born at Recorded Future. And for those of you who haven't heard of us before, simply put, Recorded Future is an intelligence company. And what we do is we track the world's threats. And threats come in many different forms. They appear through attacks, cyber attacks, physical attacks. We've heard of them through fraud. So they carry many different names, faces, and surround us. But then how do we manage to conduct such a broad task? The core lies in data. And we collect humongous amounts of it from all over the internet. And I really mean all over the internet. And we structure this data, we analyze this data, and we then present it in a more processable way to our users. And why do we do this? Of course, to protect our world and keep people safe and informed. A specific track that Recorded Future works with is that of geopolitics. And a use case that caught our attention was that of detecting geopolitical events. And today, we only do this in text. So let's look into more practical terms, how we do this. Take this data source as example, the news article presented on the screen. First off, we would start off with collecting all the data. And we see some titles, subtitles, images, you name it. We then filter out all the relevant data, structure it, analyze it to finally come to the verdict that a terror attack has occurred. Much more processable than reading the whole thing. But if we then take a step back to the collection phase of it, we clearly see with our naked eyes that there are multiple types of data, or so-called modalities, images included. Now, bear in mind, as of today, event detection is only done in text. But the images we see also carry valuable information. And sometimes this information is not caught up in the text. So naturally, we ask ourselves, how can we incorporate images in the current analysis in the most cost-efficient way? And since the paper or the workshop at which we published focused on protest event detection, that's the event we chose to focus on as well. So, without further ado, we looked into how traditionally event detection systems are developed today. And what we found was the following. Imagine having these two data sets of different modalities. The first step, if you want to conduct event detection in them, is of course to create annotations that are customized for the specific task and modality. We then use these to train classifiers that are customized for the task and modality. So essentially, methods of today rely heavily on annotations. But annotations are very costly, both in terms of time and money. And still we see them always being such high demand. So naturally we started talking, what's the reason to this? We brainstormed a bit and we came to the conclusion, or agreement rather, that we could boil it down to two main reasons. The first one addresses this importance of annotations, because at the end of the day, they are the foundation for us to create high performance, high quality classifiers. The second reason addresses the modality dependent nature of classifiers. Because as soon as you want to do a classification task, a new one, or do classification in a new modality, you need to create a new model, and therefore you need new annotations.
Yes, so we have identified the need for annotations themselves as quite a big bottleneck when developing new systems for event detection. And because of that, we of course asked ourselves how we can reduce this need for expensive additional annotated data. And considering the two reasons we found for annotations being in such high demand, we wanted to focus on the second of that, being the modality dependency within the way systems are developed. And then the question is, how can we do that? Well, we wanted to investigate if we could reduce the need for annotations by reducing the modality dependency. And the solution to that would be, one solution would be to create a modality agnostic pipeline. And that is a pipeline, simply put, that has no modality dependency. And because of that, we could be able to reduce the need for annotations. And a modality agnostic pipeline is quite a complex term, but in our use case, it means a pipeline that can carry out event detection or protest detection specifically for us in both images and text, and perform the classification independently of which of the input types that we send in. And here we see a simple image of the pipeline that we suggest to do a modality agnostic pipeline. And the key to making this pipeline modality agnostic lies in something called an image text alignment model, or ITA model. And on top of that, we have added a linear classification layer, which we train on the features that are outputted from the ITA model. So in this setup, we can send in a sample, being an image or text, and get a protest classification scores output. And the key to, as I said, making this whole pipeline modality agnostic is the ITA model. So to understand how this works, we'll explain a bit more about ITA models, since many of you here might be unfamiliar with them. And ITA models are a group of representation models that learn about visual concepts using natural text. So an ITA model should ideally understand that both this image and its caption refer to the concept of pancakes. And most ITA models consist of an image encoder and a text encoder. And both these encoders work by compressing its input, being an image, of course, for the image encoder, and a text for the text encoder. And these are compressed into feature vectors in a feature space that is shared between the two encoders. And here we see a very simplified visualization of that feature space, but in reality it is of 512 dimensions. So the way that these ITA models are able to understand visual concepts is that the encoders are trained to align specific concepts in this feature space. And this means that images and text referring to the same concept are pulled together in this feature space during training, like we see here. And in contrast, if we have an image and a text referring to different concepts, like if we had the same image but a text talking about animals, these would be pushed apart in the feature space instead. And the way that these encoders work of embedding specific concepts into specific positions in the feature space gave us the idea to use them as a type of feature generators. And we used a specific IT model called CLIP, which was released in 2021 by OpenAI. And that was almost 2 years ago now. But at the time of release, it had state-of-the-art performance on zero-shot image classification tasks. And that is all thanks to it being pre-trained on about 400 million image and text pairs collected from the internet. So now we can look back again at our pipeline with some more detail to it. And we see now we see each of the encoders added into the ITA model box. And we also know that each of these encoders output a feature vector of 512 features.
So now you've seen our pipeline and you're familiar with the end goal of reducing the amounts of annotations. So how does our pipeline make this end goal possible? And as you might have guessed, the star of the show, cross-modal transfer. And formally, cross-modal transfer is defined as the transfer of a model, so-called knowledge, from one modality to another. And knowledge we measure in terms of event detection performance. But more practically, you can say if you have a model trained on one modality, such as images, it could be used to detect events in another, such as text. And if this works, it means I only need to annotate in data in one modality and still attain a model that's compatible with both, and hence reduce my both need and cost of additional annotations. And therefore, the experimental setup was molded to test exactly this quality. And we did it by training a model in one modality and testing in the other, dividing it into two different experiments, A and B, since we had two different modalities, where in A we train on images, test on text. In B, we train on text and test on images. But let's go through in detail what we actually trained. So simply put, we only train our linear classification layer, marked in orange. The weights of CLIP, marked in green, are kept frozen. Now, this allows us to swap the encoders during test time since the feature space remains untouched. And a further benefit with it, to only train a simple classification layer, is that it's very fast and cheap, easily accessible, along with CLIP being open source and of high performance, becomes even more worth it. And of course, the training we did in 2 rounds. First, we took image samples from an image data set, passed it through the ITA model, got features, which we trained our classification layer with, attaining this image feature trained model. We did the same, but for text samples. So we attained a text feature trained model. And now we stand here with these 2 models, the pink one trained on image features and the blue one trained on text features. How did we use these to actually test the model's ability to transfer the knowledge? Let's try and visualize it. We stand here now with our pipeline and the 2 models. In experiment A, we take our image feature trained model and place it right here. And then we take our text samples, feed it through the text encoder of the ITA model, attain features. And these text features, we pass through our image feature trained model to attain a confidence score for each sample. So this setup essentially trains and tests an image model's ability to transfer its knowledge to text. And of course, we do the same, but in the opposite direction. So we take our text feature trained model, place it there, feed image samples through the image encoder, and pass those features through our text trained model. And this then naturally tests the text model's ability to transfer its knowledge to images. And what samples did we use? We took use of two openly available datasets. For images, we used UCLA's protest image dataset consisting of about 41,000 images collected from social media with around a 30% positive rate. And the labels were binary, protest, or non-protest. For text, we took use of the CLEF protest news train set, consisting of about 23,000 sentences collected from various news articles with around a 20% positive rate. The labels here were also binary, however, on a sentence level.
All right, so now it's hopefully clear what experiments we have conducted and why, and we can finally look at the results of them. And here we see a little table which we'll fill out with the results, but I'll start by just mentioning that we measure the performance in both of these experiments with the area under the precision recall curve. And that means that a high score close to 1 is, of course, desired, and a lower score close to 0 is simply bad performance. And we have firstly developed a random baseline, which acts as a lower boundary for the other results, and just to put the other results in some type of context. And then we can start by looking at the results from experiment A, being the image trained classifier evaluated on the image and text test sets separately. And when we evaluate this image trained classifier on text, we get an OGG score of 0.458, which is, of course, significantly lower than when evaluating on images. And when we evaluate on images, that result is the baseline for this experiment. And that is because what we're interested in measuring is the knowledge transfer between the modalities. And to be able to compare the performance, we of course have to know first how well it performs on the modality it has been trained on. Then we can move on to look at the results from experiment B, being the text-trained classifier evaluated on the same image and text test sets. And here we see that when we evaluate on images, we get an OGG score of 0.687. And this is only about 5 points lower than when evaluating on text, meaning the baseline for this experiment. And these two results together are an indication that, or it seems like the text-trained classifier can actually transfer its knowledge onto images without any significant loss, but not in the opposite direction. And that is a bit counterintuitive, that it doesn't go both ways. But to try to make sense of those results, we wanted to do some data analysis. And we have done quite a thorough data analysis that can't be covered in this talk, unfortunately. But we have a few examples to show you, and we'll try to explain what we found. So we see 3 randomly chosen positive examples from the image dataset here. And as you can tell, they all have a fairly similar way of showing what a protest is. And we found this being true for almost the whole dataset. So we see a few common elements in these positives, being groups of people standing up. Outside, we see buildings in the background with banners and so on. And we also realized, which is quite obvious when you think about it, that images tend to only capture protests when they're actually ongoing. You can't really capture a protest before it's happening or after. And let's try to remember that when moving on to look at the text dataset. And here we see a few examples as well, and we're not going to read through them, but instead just present what we found when analyzing the data in general. And in contrast to the image dataset, we found quite quickly that the text modality itself is able to represent protests in a much more varied way than images. It can talk about different types of protests, like a strike that we see an example of here in the bottom. And a strike where people don't show up to work can't be captured in an image. And we also noticed that text is able to talk about protests before they're happening, like the planning of a protest, and while they're happening, but also the aftermath of a protest. So with that in mind, it seems reasonable to believe that the text-trained model should have a more general understanding of what a protest can be. And that could be an explanation of why it seems like the text-trained model generalizes better onto images than in the opposite direction. So, we've presented a lot of weird concepts probably, but to wrap up what we think are the main takeaways from this talk, we'd like to just summarize. And we present or suggest that annotated protest text data can act supplementary for detecting protests in images to reduce the need for additional annotated image data. So this means, in practice, if you happen to have an annotated text dataset for event detection laying around at work or at home, and you want to also detect events in images, you could use this text dataset in the setup that we have done here to create at least a great starting point for that image event classification model. And with that, we want to say thank you very much for taking your time to listen to us today. And if you want to know more of the details of the experiments that we did, feel free to scan this QR code, which will take you to our paper, or just ask questions now or reach out for email. Thank you.
Thank you. So you never fine-tuned clip. You used the embeddings from clip directly, and then you just trained the classifier for event detection. Okay. So do you think that you will get better transfer if you fine-tune clip first on protest image text pairs?
Spontaneously, no, because clip is trained on a lot of data, and we've tried fine-tuning it, but so it has such a good zero-shot knowledge that I wouldn't say that it would be improved as such.
Okay, so you would have some kind of catastrophic forgetting or something like that.
Yeah.
That is, at least in a previous experiment to this, we saw that happening immediately when trying to fine-tune it.
Oh, really? Okay.
Yeah.
Okay. No, that's interesting. So, any questions from the audience? Okay.
There's one there.
Ah, perfect.
Hi. Yeah, hi. So my question is, just based on the fact that this is a model for detecting protests, who is the end user of this? Like, I don't mean the process, I mean the model itself. Is it governments, or and what are the ethical considerations that you have when you made a model that would potentially put people in harm's way, I guess? Thank you.
Yeah,
You wanna?
there of course a lot of ethical aspects to keep in mind when developing a model like this, since if it ends up in the wrong hands, it could have potentially bad consequences. And I guess the reason for choosing the protest event specifically was it was not like very intentional. It was more of we did find the UCLA protest image dataset, which is a publicly available dataset, so that was very easy to use. But also that the workshop that we presented at focused specifically on protests that year. So there's no intended user for this this event detection specifically. I don't know if that answers your question. No.
From of course from our end, but
Yeah.
then you can always, as any technology, you can use it for good
Exactly.
or the opposite way. But as we mentioned in the beginning, the company that we come from, Recorded Future, they conduct this sort of like event detection in general, and protest is one of them. And of course, we are the good guys, so we definitely help. We take use of it for hopefully good reasons.
We have another question here, yeah?
Yeah, I have a question. So how did you cater for biasness in this case? Did you come across any examples where you found out like the model was biased in that? Was there anything you came across like both for text and images?
Yeah, if we go back to the slide with the data sets, for the images here, there's one negative example of also a group of people standing up outside, and I'm not sure if both models or only the text model scored like high scores on that one. So it seemed like there was some bias in terms of that, if that is what you meant.
Yeah, but because I'm thinking that if someone was holding a banner in that
Yeah.
image, would it have like classified it differently?
No, I think the text model did classify that one as a positive, so it didn't like catch it being a negative actually. And I don't know if it had a banner, if the image model would say it's a positive as well. Maybe.
Okay.
I mean,
Probably.
we did do this as Kajsa mentioned earlier, that we did see the image model found similar elements, so to speak, in the images. But I mean, the image model was very good at classifying this type of the momentary instantaneous protest occurring. So if you want to call that a bias or a feature, that's up to you.
So we have another question over there, right?
Thank you for a good talk. I thought it was very nice and pedagogic. A question relating to your results, where you suggested that perhaps they could be attributed to things like a strike, where people don't pop up, so there's nothing to take a photo of. Have you tried testing that by removing those kind of events from the data sets?
I didn't catch the.
So
That's right.
like say in text, where there would be text that were related to strikes.
Yep.
But you don't have the equivalent in photos because there's
Right.
nothing to take photos of. Did you remove those samples in the text to see whether it actually had an impact on your final score?
No, we didn't try that, but that would have been an interesting example or experiment to do.
Definitely. What we did see is that the images had a specific look to it. So we didn't test to remove as such, but definitely a good future work.
Thank you.
Yep.
Thank you. Thank you, Ria Raj and Kajsa.
Thank you.